Hello everyone, welcome to lecture 7 um, course on software security. Right, so apologies for not conducting the previous week lectures. Um, Due to some situation, I was not able to conduct the lectures, but I hope you all would have gone through the lecture recordings of uh, the two lectures during the previous last to last week, right, during the Navaratri holidays. So, just a quick recap of what we covered in the last two lectures, since it's been a week, a couple of weeks break in between, right? So, in the previous lecture, in lecture 5 specifically, we looked at something called as the assembly language, and we looked at the uh, different varieties of these the instructions, right? The assembly language instructions. So let me just open up the. So we looked at the various instructions that are present in the x86 ISA. We looked at data manipulation instructions like move and exchange, push and pop, and then the arithmetic instructions, logical instructions like AND or XOR, all those stuff, and we looked at how they work, and we looked at the unconditional branch instructions, and also we looked at some special registers which are being used when we try to compare two operands, something like that, right? And basically all of these operands can either be a register operand or a destination operand or memory operand, or it can be an immediate value. And each instruction has its own set of constraints. So for example, if we take the exchange instruction, it has it cannot take an immediate value or a constant value, and whereas so the type of operands it can take, the instruction, and all those things sort of are embedded, or that logic is part of your that logic is embedded as part of your processor design, right? The core, the hardware processor implementation consists the implementation of all these instructions, and every instruction has a different has a unique opcode, and also say for example, if you take the add instruction, each variant of this add instruction will have a different opcode, a variant of that opcode, based on what type of operands it will take. So whether it takes only register operands or a mix of memory and register operands and all those things, unique opcode will be there to address, to identify which specific instruction we want to execute, and in what way are we passing those operands to those instructions, right? And these are the type of instructions we had, and this we looked into lecture 5, right? And following this, we looked at specifically the process call stack. We looked at the process call stack, and in the following lecture, and we discussed how the arguments are being passed and how specifically the stack is being used in our process during program execution. And the stack is not just for storing local variables, but also for tracking function calls and for maintaining the temporary memory for that particular active function, right? And we looked at the call-in convention for the x86, specifically the 32-bit ISA. And to have a quick gist of what the stack usually does, the stack call-in convention is when, say, main function calls another function fun1, we indicate the main function as something called as the caller, and the fun1 as the callee function. And the first step is we push the parameters, like during the call, like just that function call includes all these 8 steps, right? So the first step is I should push the parameters onto the stack. So if main function is passing, say, some 3 parameters or something to fun1, all those parameters have to be pushed onto the stack. And once that is pushed, the return address where the instruction pointer, right, should resume execution at once I have executed the fun1, that specific address where my instruction is present is known as the return address, and that should be stored on the stack, right? And once these 2 steps are over, then we sort of pass control to the fun1 function, and there it has to do some steps, that is specifically the third and fourth step. So the third step it stores the EBP register, right? So basically whenever we take a stack frame, the EBP and the ESP sort of point to where the actual the stack frame is located. So the stack is sort of a contiguous memory region and consists of many frames, and each frame is particular with respect to one specific actively executing function, right? And say fun1 is executing, my EBP register and ESP register will be pointing to that stack frame where all the local variables with respect to fun1 would be stored, and all the information whatever fun1 needs to access, right, which are having local scope, all those would be stored in that particular stack frame, right? And it allocates local variables onto this new stack frame, right? Say fun1 is having some 3 local variables, means all those variables would be allocated into that new stack frame. And once that is done, once fun1 has executed, it should return back to main function. And just before returning back, it should first deallocate all the local variables. So if it has allocated some local variables on the stack, it should deallocate those, right? And once it deallocates those, it should set the registers accordingly so that it points now to the main function stack frame, right? And once that is done, it restores back the register values and does the return instruction. And basically the return instruction takes the return address which we had stored on the stack in step 2 and populates that in my instruction pointer. So one specific register which we missed, but it's sort of uh, a very important register in x86 is known as the RIP or the EIP register. So it's the instruction pointer register. And hello Nilman. Hello, am I audible?
Yes, sir.
Okay. So have you gone through the previous lecture recordings which I have uploaded?
CAT exam going on, so I can't able to student.
Oh, right. Okay. Okay. Cool. Yeah. So um, I'll be continuing the lecture, like assuming that you have gone through the recording, right? So when you have time, you can look at the recordings. So
Okay, sir. Thank you.
right. So continuing, right? So this is how your stack will look like whenever we call from one main function to fun1 function. And now let's so in this lecture, specifically in lecture 7, in today's lecture, we will be looking at so we discussed how the stack works and all those things. So in lecture 7 we'll be looking at actual assembly code, right? Looking at the disassembly, object disassembly, and look at how that stack all those specific instructions that are being present in the disassembly to get a better sense of how the stack call-in convention and all these things work, right? So in today's lecture we'll be looking at that, and in tomorrow's lecture we'll be looking how to use GDB, so that from next week onwards we can get started with all the software experts. So we'll be using this sample main.c program in today's lecture and tomorrow's lecture as well. So it contains one main function which has three local variables a equal to 0. So if you have any queries or something, do stop me in between. I'll be happy to answer. Right? So the main function has three local variables and calls a function called fun1 and passes these three variables a, b, c to fun1, and in within fun1 what it does is it basically does the following. It calls malloc, uh, and it initializes this global pointer to some dynamically allocated memory region containing five elements of five integer elements, right? And it does a while loop where it initializes all those array elements to 1, and once that is done it again uses a for loop and prints the entire array at every element in the array, and then prints the values of a, b, and c. So nothing much of logic, right? Just printing and initializing the array contents. So now let's look at how the disassembly looks like, and we'll look at the various aspects, right? So in the call-in convention, we looked at how parameters would be passed and all those stuff. So we look at those specific instruction snippets within the object disassembly and comparing it with or associating it with the concepts that we learned in the previous week. Right? So I will compile my code using hyphen static hyphen m32, right? I get the file a dot out. I just this is the output, and I get the disassembly from a dot out. So this is the disassembly. So for now, what I'll do is I'll enable the debugging flag -g, so that it makes much better sense when I explain the disassembly output, right? So that you can easily compare, associate with the actual source code. So if you notice over here, this is the start of my main function, and I have linked the executable a.out as a statically linked executable, right? So all the library, the libc library, everything it's statically linked, right? So all the code, everything is now part of the same executable a.out. I am not using any shared libraries, right? And this is the main address where the main function is present, and this is the address where my fun1 function 1 is present over here. Where is it? Yeah, these two. So let me just copy these two functions alone to a separate file so that it makes our lives easier. Sort of. Right. So now let's start with the main function, right? So if you notice over here, this is the start of the main function, and these things for now you can just avoid, right? Specifically look at this, these three, this set of lines. So whatever I'm separating it out, the highlighted lines, right? So I'm allocating three variables A, B and C and initializing it to values 0, 1 and 2. Now if you notice, um, we are actually storing some value into the variable, right? And for that I'm using this specific instruction called the move instruction. And the move instruction, um, this is the destination and this is my source. So the source is like an immediate value. So I'm copying the values 0, 1 and 2 respectively into ABC, right? So if you notice the values in the move instruction, the source values in all these three move instructions, in hexadecimal notation it's 0, 1 and 2. And the destination is actually not a register but some memory location, right? And how do we read this instruction move dword pointer EBP minus something 0x2 is basically, so if you take this instruction, it's basically what it tells is the value 0x2 value to numerical 2, it should be moved into some location, right? Now that location is specified over here, and here it specifies dword pointer and within square brackets EBP minus 0x. So this basically mentions it's some memory location to where I should move this constant value 0x2. And that memory location, what's the address, where should I move, what's the location, right? The address where this value should be copied into is specified within this square bracket EBP minus 0x. So basically at runtime, whenever I'm executing the program, whatever value my register EBP has, that value minus 0xc will specify the location, the actual address location where I should copy this value 0x2. And this specific keyword dword pointer is nothing but it specifies how much value I should copy, right? So what's the size of the value I should copy? So whether I should copy just a byte or I should copy 2 bytes, 3 bytes or something. So dword pointer is basically it copies 32 bytes, 4 bytes from the source into the destination, right? So if you say if your memory, say if EBP register has the value 0x 1000C, right? So now at address location EBP minus 0xC means it is address 0x1000, okay? And so at address 0x1000 it will copy this value 0x2, right? And say in Intel architectures, x86 ISA, everything is byte addressable, right? So at every single byte I can write any value. So at 0x1000 it will hold 1 byte of information, 1001 holds 1 byte. So up till 1003, from 1000 to 1003 it will hold 4 bytes. So by specifying dword pointer, right, basically I will be copying this value 0x2 within this 4 bytes of information. So what happens is the information, it will be copied like this 0x2, 0x0, 0x0 and 0x0. So the entire so this whole thing 0x2 will be sort of repended with zeros and filled up with 4 bytes write space and copied, and all these addresses 1000, 1001, 1002 and 1003 will be set to that specific value whatever we specified over here. And similarly for move dword pointer EBP minus 0x10, the value will be copied as 0x1, right? So now say like initially before I execute this move instruction, right, EBP minus 0xc, this was the third move instruction, say at the addresses 1003 it was say 2 and say it was 3 and 4 and some other number 7, right? So before the instruction executes it will be something like this, but after it executes, right, it will be changed to 0x2, 0x0, 0x0, 0x0. So basically this 0x2, even though it's just 1 byte value, right? It's basically 0x0002. So it's 4 bytes value actually, which is copied into my destination memory location, right? So instead of dword pointer, say if I have something like a byte pointer, right? What does this mean is, now instead of copying 4 bytes into the memory location, it will copy just 1 byte. So now what will happen is, say initially the values were 2743, it will let it be like 4743 means my 2 will be copied into the address 1000, location 1000, but the remaining values will be as it is the same, right? So depending on the keyword that I use over here, whether it's dword or byte or word, the number of bytes that will be copied from my source into the destination will vary. So mostly, here dword pointer specifically in x86-32-bit ISA, dword pointer, dword, right? Dword refers to 4 bytes size, that is 32 bits. If it's just byte means it's 8 bits only, 1 byte. Word means I guess 2 bytes. 2 bytes will be copied, right? And yeah, that's it actually. So um, all the variables A, B, and C are present in memory location, and their address wherever it's present is sort of stored within this EBP register, and the uh, the specific address where they are stored, the variables A, B, and C, is present in these values. Like EBP minus 0x14 is where the variable A is present. EBP minus 0x10 is where the variable B is present. So to those memory locations, I'll be copying these values 0, 1, and 2. So this is what the move instruction actually does, and how we should read these move instruction is, the byte specifies the number of bytes I should copy this keyword, dword, or byte pointer, and this pointer over here, this specifies the address location, right? And this is sort of runtime computed. At runtime, whatever that register has, that value minus 0xc will specify the address where uh, I should be copying the data in. And you might ask a question, why specifically I should use the register EBP and not say some other register like EAX or something, right? So this is where my calling convention comes into picture, like the x86 ABI, right? x86 32-bit ABI. So by ABI, so you might have heard of the term API, application programming interface, right? So say whenever you use some third party, say some Python ML library or some GPU graphics library, something, they will be exporting their programming interface, the functions that you can call and to use their functionality, right? All those API features, the API documentation. So that is with respect to an application and what you can do with that application. So there is this concept called as ABI, and this ABI sort of specifies, it's not like a rule, but it's something that it would be good if we all the languages or the programmers follow this ABI. And here ABI is application binary interface, right? So when we take a binary, like we have all these registers, 16 registers, right? We have registers like EAX, EBX, ECX, CDX, all these different registers are there, ESP and EBP, and all these different registers are there. Again, they are like um, unnamed registers like E9 till E15, something like that, E8 till E15, right? Something like that. all these registers are there, but what's the use behind these registers? It provides these temporary scratch space, but why some registers are named and some registers are not named, right? So there is like this meaning behind them, right? So ESP and EBP registers are sort of used for marking your stack frame, marking your active stack frame, and EAX register is used for return value from function and all those stuff. And ECX and EDX registers, they were used in multiplication operations, and EBX also, I guess, right? So every register has sort of some, especially these named registers, they have sort of some semantic meaning attached to it, and this usually comes under this concept of application binary interface. So what all we learned in the previous lecture about the call-in convention also falls under this ABI, right? It's not a standard rule that you should follow this ABI as it is always, right? So say I'm inventing a new language, I'm writing a new language called Java++, right? I can write a compiler, I can compile my Java++ source code into a binary, and I can ensure that the compiled binary, right, the binary that I emit from that new compiler, whatever I have developed, it sort of does not follow this call-in convention which the other languages follow, right? So I can, instead of using ESP and EBP for marking the active stack frame, I can use EAX and EBX, and instead of EAX as the return value from function, I can use ESP. This can be done, but the issue is this will not help my language to communicate with other languages, right? So when you take Java or Python, it usually does not execute on its own, right? All the code, it cannot be, you cannot code everything in just a single language, right? With the plethora of applications and use cases that you have in this real world scenarios, you will be using multiple languages. So for accessing databases, you will be using some query language. For web application, you will be using these markup languages in JavaScript and those stuff. And for low level functionality and for this driver, um, uh, uh, the hardware drivers, right? All your I/O device drivers and all those things, you will be using C language for speed and uh, low level functionalities, accessing raw pointers and all those stuff. So different languages should be able to communicate with each other, and also moreover you will be using third party libraries. So even if you are just using a single language like C, you won't be uh, coding the entire application on your own, right? You will be using some third party library or some external library, link it with your application. So even in a normal hello world program, you are using this flag stdio.ht, you are including that header file. So basically you are including some functions present in a third party library called libc, which is part of the GNU compiler collection, right? The libc library, libc. So all your printf, scanf, file read, fwrite, and all these functions are, that actual implementation is defined in that libc library. So that library is included with your source code. So if in my disassemble, if I look for say the function fread or something, it should probably. Okay, so for example, I'm doing a malloc, right? So where is this malloc actually present? So this the function where my malloc is present, and if you notice that function name is libc malloc, right? So all these things are there, right? So for example, if you notice in fun1 function, I am doing a call to malloc, and if you notice the actual function name which it's calling, it's libc malloc. So basically the malloc function is implemented as part of this libc library. So now to communicate with other libraries, who have written some code or something, right, who have written that C code. If you are not following your specific C code binary is not following the ABI, it becomes sort of a tricky issue when you have to communicate with other functions. So this call and convention and all this ABI sort of help for helps in these compatibility issues when you want to communicate with different functions or even across languages, right? It sort of helps. So in this specific three instructions, the move instructions, if you notice, we are using these registers EBP only. So why not some other register like EBX or something? The reason is you should notice the scope of these variables A, B, and C. So the variables A, B, and C are of local scope, right? So local scope is whenever the function executes, they will be active, and when we return from that function, those local variables will be out of scope. So basically, we should deallocate those variables, right? So when we take a malloc when we take some global variable, the scope is global scope, right? Because it's active throughout the program, the process lifetime. It can be accessed from anywhere. Whereas these local variables are sort of local to that function, and only that function can access, and no other function is allowed to access. Or it doesn't make sense if other functions access, right? So those are all local variables and it's local scope. And um, so when we say these functions malloc and free, right? So malloc is you allocate it on the heap, and free is you free it from the heap memory, and this is with respect to dynamic memory management. So whereas in local variables you don't use any such function like malloc and free, you don't call any function or something like malloc to indicate that it's like a local variable, right? So then how does that allocation and deallocation happen automatically? It happens via this concept of stack pointers. Stack pointers. So basically when you execute a function, so when you execute a function, say currently it is say some it has not yet started execution, right? So this is the top of the stack, and the stack goes downwards, and it has to start executing the main function. So let's say main is executed. uh, Currently execution is in the main function, and now it's invoking say fun1. So basically what happens is, whenever we call a function, we have to allocate some space on the stack which identifies the stack frame for that function whatever is being invoked, and this stack frame would be used to store all your local variables and all those stuff. So this we would have discussed in the previous lecture, right? And that stack frame, the bottom of the stack frame, right, wherever it's located, it's represented by the register EBP, and the top of the stack frame, so actually the top should not be here, the top of the stack frame, right? This will be represented by the register ESP, right? And this ESP will sort of be moving always up and down whenever we delete or insert new stack frames. So this stack frame, this specific, so let us name the stack frames stack frame 1, and this is stack frame 2, right? So stack frame 1 is with respect to the main function, and stack frame 2 is with respect to the function 1, right? And whenever one finishes execution, this stack frame will sort of be deleted. uh, Deletion as in I'll just be moving this ESP register. So my ESP register will be pointing to the top of the stack, right? It will be pointing to the last used, uh, actively used region, the memory region in the stack memory region. And when I just change this ESP value to point somewhere over here, that basically means, and my EBP to here, right? If my EBP and ESP change, that basically means I've lost access to this memory which is being used by fun1. And when it resumes execution and main function, basically this memory is now active. So the takeaway is the registers EBP and ESP are sort of, um, specifically the EBP register, we call it as the frame pointer. Right? So the EBP register is the frame pointer. So within your stack frame, so the main, say main function stack frame. So within that stack frame, if I have to access any of its local variables, so within main function you will have the variables A stored, B stored, and C stored with the values 0, 1, and 2, right? And all the addresses, whatever you have for A, B, and C, they are all somewhere pointing into this specific stack frame 1. So the EBP register sort of helps to identify where the local variables are stored, because the EBP register, whenever main function is executing, will be pointing to the base of that main function stack frame. So that's why in the code, if you look at disassembly, the address, in order to find the address where A, B, or C, the local variables are found, right, are present, we'll be using the value the EBP register to find the address at some fixed offset, right? So if you notice, at EBP minus 0xc and minus 0x10 minus 0x14, the variables A, B, and C are located, right? And so all these values are sort of present within your stack frame corresponding to the main function. So if I just so if you take this as your EBP register, right, if it's pointing to over here, so if you take your EBP register and if it's say pointing to 0x1000 C, so this is my value and this value is over here, right? So this is 0x1000 C. Okay. So in that case, my so EBP minus 0xc. So actually this will be the higher address and this will be the lower address, right? And my stack grows downwards. So EBP minus 0xc and right, so somewhere in this location and the opposite order. So EBP minus 14, right? So A will be over here, B, and then C. So in this order, somewhere in the stack frame 1, which is corresponding to the main function, all my local variables are present. Okay, and so that's what we denote by these addresses, and that's why we specifically use the registers EBP. So now say if I am not storing it in a local variable, say I am storing it in a global variable. So for example, let me just add a statement int GLB, right? and let's say access GLB equal to 5, right? Let's see how the code changes. So if we look at the main function, this specific line GLB equal to 5. So now if you notice, right? So now if you notice, the ABC move instructions are pretty same. It uses the EBP register, but for GLB equal to 5, you will notice that I'm not using the register EBP, whereas I'm using some register, can be anything. Here I'm using the register, the compiler emits the instruction such that it's using the register EAX to store the address where my variable GLB is located and where I should be copying this value 5 into. Right? And notice it's not using the register EBP. And before this move dword pointer EAX comma 0x5, it's storing some value initially in this register EAX. So this specific value is actually the address, the actual address where my global variable is present, the GLB variable. So this address is first it's moving into EAX register, and then it's specifying that this is where the value 5 should be placed, and it should be a dword pointer. That is 4 bytes should be placed. So now instead of int, if I just specify character, right, it's just 1 byte, right? Int is 4 bytes. So now if I change the code and let's see what the disassembly looks like. Now if you notice, all are the same except it has changed from dword to byte. So character is, the size of character is just 1 byte, right? So I should just copy 1 byte only. So that's what it specifies over here, move byte, and the pointer location, the address location is present in this register EAX. So why not EBP register is being used? It's because EBP is exclusively to point to the stack frame, right? It's a frame pointer, and it's used to locate your local variables or anything else within your local stack frame. Any global variable access or something, or if you are trying to access the heap location, it requires access, it does not use the EBP register, it uses any other register. Right. So this is with the move instructions. Now coming to how my function is being called, specifically fun1, right? So I am calling my fun1 function. I am passing these variables a, b, c. Right? So now how do I pass these variables? As we discussed in the previous lecture, all the variables are passed via the stack. So basically I copy all the arguments, whatever I need to pass to fun1, I make a copy of that onto the stack, right? And from the stack, the other function, the callee function fun1, will read those parameters from the stack and do its computation, right? And the order in which those variables would be passed is in the opposite order. So first, say if I'm passing A, B and C, means first it will be pushing C, and then B, and then A. So notice over here we have these three instructions. Right, for now just don't see this instruction. Right. So we have these three instructions: push dword pointer EBP minus 0xc, and then dword pointer EBP minus 0x10, like that. So basically what your push instruction does is it pushes whatever value. So over here if I'm specifying say some register or some memory operand, so how we should read this instruction push dword pointer EBP minus 0xc is pushes it onto the stack, and while pushing it, what it does has some side effects, right? So basically it will change your ESP register. So my ESP will now be updated to ESP, since it's growing downwards, right? So ESP will be updated to ESP minus 4, right? So that's what the push operation usually does. So minus 4 is as in the sense, starting from a higher address, if I keep on pushing right onto the stack, my stack grows downwards, and the top of the stack, that's what my ESP is pointing to. So that will keep on decreasing that value. So like here, right? So if I again pass some value onto the stack, so initially if ESP is say 0x1000, something like that, means if I'm pushing again, my ESP will go down. This will be ESP new, and this will be 0x999c, sorry, 99c, right? So this is what the ESP pointer would be decrementing, right, when you are pushing onto the stack. And what am I actually pushing onto the stack? What value is being pushed? That is present over here. So it can either be a register, so or it can be a constant. So if I just mention 0x1, it means I'm just pushing the value 1. If I mention say some register EAX, it can be I'm pushing the value found in this register EAX, or else I can specify any memory location, right? So it will access that location, get the value present at that location, and push that value onto the stack. So over here I'll using this I'm using a memory operand. So how do we read this memory operand? Is same how we read this move d word pointer instruction, right? It's pretty same. So what is the value that I should push? The value that I should push is present at the address pointed over here. So at runtime, whatever EBP register is containing, minus 0xc, that's the location, and the value present at that location, starting from that location, 4 bytes of value that's specified in this const keyword d word, right? 4 bytes of value will be pushed onto the stack. Right? So if you notice EBP minus 0xc, this is where I had actually placed my value 2 into variable c. So this is where variable c is present. So by push d word pointer EBP minus 0xc, it basically means I'm pushing this variable c onto the stack. And similarly, the other two instructions are pushing the local variables b and a onto the stack. And once this is pushed, this is what is mainly with parameter passing, right? So this is how parameters are passed onto to function 1 via the stack. So I'm making a copy of the parameters, pushing it onto the stack, right? And finally now I should be calling the function. So the call instruction I'll be using over here. So the call instruction logic is, it will it also does have some it has some implicit logic. So the logic is basically it pushes the return address pushes the next instruction address onto the stack, and control flow jumps to fun1. So this is where the address where my fun1 function is located, and before the control flow jumps to, right, whatever is the next instruction address, right? So sequential next instruction. So this is the currently executing instruction. The next instruction is actually this, right? If I don't have a jump to fun1, the next instruction it should execute is basically 8049 DE2, which is a add instruction. So instead of doing the add instruction, it's jumping to this function 1, fun1. So when fun1 finishes execution, it should resume execution at this specific point in main function. So that is what it means by pushing the next instruction address onto the stack, and this instruction address is basically my return address, right? So when fun1 returns back, where should it return to? The return address, specifically some point within your main function. Right, this it pushes onto the stack, and the control flow jumps to function1. So this is what happens when I call a function fun1 ABC. It pushes the parameters and calls a function1, and the call instruction itself, the logic is it pushes the return address onto the stack. And now if you look at fun1 logic, let's see what fun1 does, right? So fun1 logic, this is fun1 logic, right? So for now, let's leave out this specific instruction NBR32. Now let's look at this instruction. These set of instructions, let's look at. So the first instruction is something called as the push EBP instruction. It has inserted, and then we have move EBP ESP, push EBX, and then sub ESP. So these specific instructions, right? These set of instructions is something called as function prologue. Right. So function prologue is basically some set of code, set of instructions inserted always at the start of a function, right? So if you have some text or something like a prologue and epilogue, means always there will be some standard format before you write some document like a header or something, right? So similarly, irrespective of what your function does, whether it has a, excuse me, so whether it has whether it does Fibonacci computation or quick sort or merge sort or anything, at the start of the function and the end of the function, there will be a set of instructions to set up the stack frame and all those stuff, and to return back to main function what all it has to do properly. It has to do some logic of some set of instructions are done, some predefined set of instructions which are sort of automatically inserted by your compiler when it's compiling your source code. So these instructions are known as the function prologue and the epilogue. So prologue is at the start of the function and epilogue will be at the end of the function. So the prologue and epilogue is what it does. The main task of these instructions is, one, it should set the um, it should save all the registers, save the important registers, right? Save the important registers, and what we know term these are like callie save registers, right? And then allocate some space on the stack, allocate the stack frame, right? Allocate the stack frame, and that's the function prologue. And the same way, the epilogue is while exiting the function, and that's the opposite. So it saves the callie save registers onto the stack and restore the callie saved registers from the stack into the registers, like popping it back into the registers, and this is deallocating the stack frame, whatever it had allocated. So this is what your function prologue and epilogue is tasked to do, right? And so let's look at the set of instructions which the prologue and epilogue will usually do are as follows. So first thing, I've introduced a term called callie saved registers. So what do I mean by callie saved registers? So if you notice, right, I have mentioned the application binary interface, the ABI, and we would have seen that ESP is for the stack pointer. Okay, EAX is for something else, return value and all those stuff. So out of these registers, or all your 16 registers, you have just finite number of registers, just 16 registers, and every function is allowed to use those registers in every way possible, right? Pertaining, assuming they follow this binary interface. Now we saw that ESP and EBP registers. So EBP is the frame pointer and ESP is the stack pointer. But we also noticed that this EBP register will point to the currently executing stack frame. So say if my main function is executing, one second. So say if currently your main function is there and it has this stack frame 1 allocated, my EBP will be over here, right? Now I should, when I am calling a new function, function 1, I should allocate a new stack frame for this onto the stack where I can store all the local variables for computation, the all those things, and my EBP should now point over here. This is what my new EBP should be. But to do this, right, I will be overwriting my EBP register. So basically, if my previous value was say 0x1000 C, now I should be overwriting with some 0x 950, something like that. So what will happen to this old value 1000C? So when I, after executing func1, when I return back to main function, my when I return back and when I execute whatever instruction is there, so we mentioned, right, I should come back to this instruction and continue executing, right? Um, so when I return back to main function and continue execution at the return address, whatever is pushed onto the stack, my EBP register will still be the new value, whatever is associated with fun1, right? So it should be changed back to 1000C. So who will change that back? Well, I should restore back the EBP register. I just have one register only in the hardware, and I'll be reusing that register for every function pointing to the actively used stack frame. So all the values, the previous past values of the EBP register, I should store it somewhere so that when I keep on returning back, right? So this is just like one function, right? So say now I have like a chain of functions I'm calling. Let's say I'm calling like main calls function 1, this calls function 2, this calls function 3. So during every function's execution, I will be using the EBP register to point to its stack frame, and that stack frame, that EBP value I'll be using. So when I return back to the previous function, I should restore back that EBP register value so that it executes properly. So if I don't restore back the EBP value, what happens is all access to my local variables will be happening via this register EBP, say EBP minus 0xc or something. So it will all be like a mess, and you won't get your proper values, right? So to um, uh, so what the API does is it tells the compiler that some registers are to be um, deemed as callee saved registers, right? And what I mean by callee saved registers is callee saved registers is, um, out of the 16 registers, some are callee saved, especially the registers EBP and um, the EBX and those stuff, right? I'll be sharing the ABI link and those things. Right? So the callee save registers, basically what it means is it's not up to the caller. So if main is calling fun1, right? Main does not know what registers fun1 will be corrupting or not, right? So say fun1 won't be using the EBP register at all. Say it doesn't have any stack frame at all. It's not using any stack frame. So in that case, it won't be using the EBP register at all. So in that case, the fun1 need not save the value of EBP into some temporary location, the old value of EBP, and corrupt it. It doesn't corrupt it, right? So it does not save it anywhere. But say if it needs to change that register value, uh, the callee save registers are a set of registers, right, out of these 16 registers, where the callee function should save the registers before using them, before writing to them, right? So basically, when before I'm using the EBP register for my own use, I should be making a copy, the old copy of that register into the stack, so that at later point at function epilogue, or at the exit point, right, I can restore back the value. And basically what this means is, at the start of the fun1, say the main function is calling fun1, right? So for example, EBX is a callee saved register, right? So say when before during the main function's execution, EBX has the value 15, let's say 29, okay? And during fun1 is executing it, what it will do is it will save this 29 onto the stack. It will save it onto this stack, this value 29. It will use this EBX register for some other purpose. It will store the value 99 or something like that. And at the epilogue, before exiting the function, before the control resumes to the main function, right, it will restore back the value 29 from the stack into the EBX register. So now when main function resumes execution, right, from the perspective of the main function, what all registers the value it had, right, before control passed to fun1, all those registers will be having the same value. So that's the guarantee that fun1 provides by these callee saved registers. So basically all these set of registers which are supposed to be callee saved is a guarantee that my callee provides to the caller, fun1 provides to main function, that I'll be using these registers, but before using those registers, I'll be saving those registers onto the stack, so that when I return back execution to your function, these registers will be having the values which you had returned finally, right, before you invoke the fun1 function. So this is the concept of callee saved registers. There are a set of registers called caller saved within this out of the 16 registers itself. Some are callee saved, some are caller saved. So caller saved registers is the main function. The caller does not expect the callee to save this register. Instead, it itself saves these registers. It itself saves a copy of these registers value onto its own stack frame and passes control to fun1. So now fun1 need not worry that it will be corrupting those registers, and it need not worry that it should save those registers onto its stack frame and restore it back when it returns back to main function, because the main function itself would have stored a copy of these register values onto its own stack frame before it even invoked fun1 function, right? So this is what caller saved and callee saved registers are. So this will be sort of like a little bit new to you, like if you have not um, come across this concept of caller and callee saved, but This will be helpful whenever you look at some code, assembly code specifically, to understand why you will be like pushing some registers simply onto the at the start of the function logic, and why you are just popping some registers without no reason, right? So this is the reason. Some registers, the caller function expects the callee to save it in its own stack frame. Some registers, the caller function saves it on its own. So this is what we mean by caller saved and callee saved. And again, the what register should be callee saved or what should be caller saved is given in the ABI, but it's up to the language designer, the compiler designer, to decide whether you should have callee saved or caller saved. So I can have a compiler which can have zero callee saved register. So basically, everything will be caller saved. So everything can be caller saved registers. So um, the main function, when it calls fun1, it will not expect fun1 to save the registers. Instead, main function will itself save all the registers onto its own stack frame. So when I mention the main function saves in its own stack frame, whereas fun1 saves in its stack frame, right? So it depends on where I'm storing it, right? So caller saved registers would be stored over here, caller saved registers, whereas the callee saved registers would be stored in this area of the stack frame. So whether it's in the main stack frame or the fun1 stack frame, it depends whether it's caller saved or callee saved. And depending on the language designer or the compiler designer, the number of which registers are to be caller or callee saved is flexible, right? But the x86 ABI sort of specifies some set of registers to be callee and caller saved, right? So coming back to the function prologue, right? So we looked at the prologue will basically allocate the stack frame and save these callee saved registers onto the stack. So that's what is happening over here. So if you notice over here, the first two instructions is basically it copies the it does two things, right? It copies the old value of the EBP register, that is the starting the main function. So when main is calling function 1, let me just draw it and show. So initially, let's say EBP asset uh, 0x1000, and this is your main function, and fun1 is executing, right? So before it changes the EBP to this specific value, what it will do is it will store the copy of EBP over here onto the stack. So 0x1000, it will store it onto the stack, and let's say this is where this is 0x950, right? So it will get stored over here, and now what it will do is my ESP has keep on updating. So my ESP value is something over here. ESP is the top of the stack, right? Right. So my EBP value is stored over here. My original EBP value is stored over here 0x1000, and ESP value is updated. So now it's pointing to 0x94C, right? Minus 4 bytes. Now I should change this EBP register such that it should point to this new stack frame, whatever I'm going to allocate with respect to function 1, right? So this I'm basically this equal to I'm moving this ESP register value into my EBP register. So that is move ESP comma EBP. Sorry, EBP comma ESP. So the ESP into EBP I'm moving. So first I place the original value, the value corresponding to the main function's frame pointer. I'm making a copy of that onto the stack frame so that when I resume execution at main function, I should use that value, right? And once that is done, I copy the value, the current top of the stack, which demarcates. So whatever I'm going to write over here in this location is going to be the local variables of your fun1 function. That is local variable, the stack frame of fun1, right? So the starting of that stack frame, the base of that frame is esp currently due at runtime. So that value I am passing it, storing it into ebp. So now my ebp is pointing to the start of the stack frame, which is associated with fun1, right? And if you look at the next instruction, there is this instruction push ebx. So ebx is a Kali saved register, and before I'll be using the ebx value in any way, right, I'll be saving this into the stack frame of fun1. So push ebx means again esp will be updated. So esb will be updated over here. Sorry. So this will be my EBP, and now EBX will be pushed over here, and this will be my ESP. And from here onwards, from this onwards, this is stack frame 2 with respect to fun1, right? So this is what these two instructions, these three instructions represent. And then we have this instruction sub esp 0x14. So when we do sub esp 0x14, it's basically I am changing the stack pointer to something over here. So now my stack pointer points to ESP, this value. So say it's like initially it was some value like 944, now it is 930, right? And it will be pointing somewhere over here. Right, this is my new ESP. And why did we do sub ESP? That's basically to allocate some space for the local variables on the stack frame, right? So if you just do an analogy, right? We do this malloc function to allocate some space on the heap, right? So here sub ESP, this specific instruction sub ESP 0x14 is you are allocating some space on the stack frame by manipulating your stack pointer register, which is pointing to the top of the stack. So if you decrement your stack pointer register, it basically means you are allocating some space, right? Since it denotes the last active region referenced region that can be used by the process on the stack memory, right? So the lower the register value of the stack pointer, more the memory, right? So if you decrement the stack pointer, you are basically allocating something on the stack, and if you are incrementing, if you are doing an add ESP, you are decrementing. So this is what your prolog would look like, the function prolog. And the remaining instructions are all actually part of the logic of the function, right? The Fibonacci function, the fun1, the printf, for loop and while loop and all those stuff, right? And once it's done, if you look at the end of the function, so if you notice this closing brackets, closing parenthesis, you'll notice some 4 instructions are there, and this is what is actually the function epilogue. And specifically, if you notice, you will see that whatever instructions we looked at function prologue, right, the opposite of these instructions will be taken in the opposite order, will be present in the function epilogue. So we pushed the EBP value and we updated the EBP register, right? We'll be doing the opposite, that is we'll be restoring back the EBP value from the stack wherever we had stored. So we had stored the original EBP over here, right? 0x1000 onto the stack. This we will be again returning back to the EBP register before we resume execution in the main function, right? And the values push EBX will be popping that also, and then we should be deallocating the local stack frame and then finally the return instruction. So that's what happens over here, right? Uh, so if you notice this instruction also, so this is my add ESP comma 0x10. So if I just so add ESP 0x10, right? So initially I would have done sub ESP 0x14. So in between I would have deallocated some memory. So let's say assume 14, right? So whatever I have subtracted from the stack memory, the pointer register, that is I have allocated. If you look at this diagram, I would have changed ESP over here. So I will just highlight this, right? So I have changed my ESP from here to here, right? ESP, the new ESP. From here to here, I would have changed it. But now this is what is allocated. Now when I deallocate, I should do the opposite. Now my ESP should now again be this new value, the previous value present over here, 944. So I should just add whatever I had subtracted previously. I should just add that same constant. Right? So that's why I have this instruction add ESP. And followed by that, if you notice, I should now restore back my EBP register, right? Whatever the frame pointer is with respect to the main function, whatever I had stored on the stack before at the function prolog while entering fun1, that value I should be returning back to my EBP register. And before that also the other callee save register, whatever I've used, I should be restoring that also. So if you notice, right, I had have done push EBX somewhere over here. So if I just copy this function prolog, the function prolog, I just, so line by line, if you just notice, first in the opposite order it goes, right? The stack is last in first, so it basically goes in the opposite. So the last thing that I did is allocate the stack frame. So the first thing I should do is deallocate that stack frame. That's the first thing I should do in the epilogue. And then the thing that I did in the reverse order in the prologue is I push the callee save register EBX. Right? Now I should pop the register, pop that value from the stack onto the register EBX. Right? I should restore back the content of EBX register. Now where is EBX register is present, right? If you notice the stack location, my EBP is say present at location 94C mains. That's where my fun1 is present, right? So this is where my fun1 is present. The frame pointer with respect to fun1 is present in 94C, and the first value it is having is EBX register. So the starting of that value is 94C minus 4. That's the starting address, right? So at that location EBP minus 0x4 is where my EBX value is being stored on the stack. So that I will be moving from the location, whatever value is being stored at this location, 4 bytes of value will be moved into the EBX register. So this is actually reversing whatever I had done in the prologue, that is push EBX. So I have restored my callee save register, I have deallocated the stack frame. Now once this is done, I should be doing the reverse of these two instructions, right? So whatever the old value of EBP was, I should be reversing that. I should be restoring back. Now, so basically, if it's my EBP is say 94C, I should change it back to 1000, right? And the leave instruction is like a concise instruction which x86 uses. which basically does the following. It does the opposite, right? So it moves um, what it does is it moves the ESP into it um, EVP into ESP. Yeah. So here I'm doing move EVP comma ESP, right? It does the opposite. It moves ESP and EVP value. So basically, this is where my uh, previous EVP register with respect to main function is present, right, at the start of this stack frame, right, previous of the stack frame. So if I just look at the actual address contents, so if you just draw it again, right, so for a bit of clarity, so this is my initial stack frame 0x1000, right? You will be storing 0x1000 over here, and say this is 94C, right, 0x94C, and this is where my EVP would be present, and this is where EBX was stored, and all your all your local variables. So I have deallocated this, and I have popped I have moved this, restored this variable. Now my goal is to change EBP to this specific location, that is 0x1000, right? So this value should be going into my EVP register, right? So to do that, what the logic is, right, it does the opposite. So here it did move EVP comma ESP, and then push EVP, and then move EVP ESP, right? Now it does the opposite in the reverse order, that is move ESP comma EVP and then pop EVP. So basically, say my ESP is present somewhere over here. I change this ESP to point wherever my EVP. So both my ESP and EVP are now equal, right? Now what I do is I do pop EVP. So pop EVP is whatever is at the top of the stack gets popped into this register, whatever I have specified, right? So I'm popping the value on the top of the stack. So at the top of the stack, after deallocating all your stack frame, is what my previous stack frame pointer value is, right? That is 0x1000. Now when I do pop EBP, this value 1000, this value is popped into the EBP register, and EBP becomes 0x1000, which is main function's pointer again, right? And once it is done, I finally do a ret instruction. Return is basically I would have pushed my return address somewhere over here. My return address will be present over here. This return address will be at the top of the stack. So when I do a pop EBP, my ESP from here, from this location, my ESP will move to this location. Now at the top of the stack, you will be having the return address, and this return address will be used by the ret instruction. It will pop this return address and load it into the register EIP, and basically this return address will be this specific address value. So the execution resumes back at this instruction within your main function, and the return value, say the function one, fun1 is returning back some value, right? Say in this main.c, it's not returning anything, say it's returning 9 or something. It will basically populate that value in the register EAX and return back. And the first thing that the main function will do is use that register, copy that return value into the stack for later computation. So this is what happens during a function call, and we looked specifically at what type of instructions are being used, right? And we came across a couple of new terms, that is function prolog, epilogue, and this call is saved and caller saved registers. So this will be sort of confusing if you just try to learn it theoretical or like by heart, right? I suggest you write a small hello world program, or just use the same main.c code and execute it. Look at the disassembly and just follow the lecture snippets, like whatever I highlighted, right? And try to draw the stack frame on a piece of paper. Try to visualize it, and it will make better sense when you visualize it in this way, right? So now if I just like a full overview whatever we had discussed, right? If I just draw it and show. So if initially this is stack frame 1, and this is 1000, and this is 950, right? And this is where your return address will be stored. This is where your variables A, B and C will be stored, and this is specifically with respect to your function parameters that you are passing to fun1, right? And on top of this you will be having the actual variables A, B and C, right? So you will be having C, B, A. This is different. This is your local variables. So you will be having your local variables over here, right? And this is the parameters that you are passing to fun1. And when you do a call instruction, the return address will be pushed onto the stack, and then in the function epilogue of fun1. So up to this point, this is your main function, and following this is your fun1. And fun1, the first thing it does is it will store the value 0x1000 over here, and then it will update the EVP to over here, right? So my EVP will basically be 0x94C, and following this you will be having your callie saved registers, say EBX and other callie saved registers, and followed by that you will be having your local variables with respect to fun1, right? Now a key thing to notice over here is with respect to fun1 EVP, right? So fun1's EVP minus 0x4 or EVP minus 0x10 is where you will be having your callie saved registers and local variables all present. Callie saved and local variables and all these things. EVP plus at exactly EVP will be your old frame pointer. I mean the location, right? The value present at that location. This will be your old frame pointer, right? And at location EVP plus 4, this will be where your return address is present. So this sort of things you should sort of remember, right? It will come in handy when you look at the code and try to come up with exploits. So EBP, if you take any stack frame, EBP is the frame pointer at the start of pointing to the start of the frame. EBP minus 0x4, those things will be containing your local variables, right? Downside, right? And at EBP it will be containing the exact location of EBP value in the memory location, stack memory location. It will be having the previous functions frame pointer, and plus 4 bytes it will be having the at offset plus 4 it will be having the return address where it should resume, and above the return address will be the parameters whatever main at the caller had passed to the callie function. So this is how you should visualize this function call, right? So now so this is the end of this lecture. So we looked at the calling convention, the practical, all the instructions, and we looked at the disassembly, and we got a better understanding of these of this calling convention followed by x86 32-bit ISA. Now let's wrap up this lecture, and tomorrow's lecture we will get started how to use GDB, the debugging tool, which will be very useful whenever we try to inspect the process runtime memory contents and all those stuff. We'll be going through GDB and how to use GDB, and also a couple of extensions and the commands to interact with the GDB. So it will be like a practical session, right? So thanks everyone. Let's meet tomorrow at 4:30. Thank you.